In this video, we're going to look at something called an empirical formula. Empirical formulas are just formulas that have the simplest whole number ratio of elements. This usually applies to ionic compounds. We always report an ionic compound as the simplest repeating pattern of the crystal. So we are looking at simple ratios in ionic formulas. Now, if I look down at this problem here, I have percent composition data. I want to determine the empirical formula of a compound that is about 38% potassium, about 13% nitrogen, and about 47% oxygen by mass. So in the last couple videos, we were looking at determining the percent composition. Now it's flipped. We're given the percent composition, and we want to determine the formula. Well, I at least know what elements are going to be in this formula, so I kind of know a general formula. It'll be like potassium something, nitrogen something, oxygen something. I know the elements, I just don't know the ratio of those atoms. How many atoms of potassium to how many atoms of nitrogen and oxygen. So we somehow need to take this percent composition data and turn it into a unit that will give me a ratio of atoms in this formula. Piece of cake. Here's what we're going to do. We're going to assume a 100 gram sample. If I had 100 grams of this compound and 38.67% is potassium, then I could say that this compound is 38.67 grams of potassium. And if I had a 100 gram sample, I could say that it would have 13.85 grams of nitrogen, 85 grams of nitrogen, and I can do the same with the oxygen. If it's 47.48% oxygen, I'm going to say there would be 47.48 grams of oxygen in this sample. We're going to assume a 100 gram sample just because it's easy. If I have 100 grams and it's 38% potassium, I know it's 38 grams potassium. So we can take these percentages and directly convert them to grams. Easy. In theory, you could assume whatever sample size you want. You could say that you have a 126 gram sample, but then you'd have to multiply 126 times 0.3867 and get the mass of potassium, and you'd have to do the same thing for the nitrogen and the oxygen, which is why we usually just assume 100. It's easy. Then those percentages directly convert into masses. Okay, so grams. Great. However, the ratio in a formula is not a ratio of grams. If I look at H2O, it doesn't mean that there are 2 grams of hydrogen and 1 gram of oxygen. Those little subscripts in a formula are a ratio of atoms. It's 2 atoms of hydrogen for every 1 atom of oxygen. And that comes to the ratio that we need to get a full outer shell or to share electrons. So I need to convert this again. I can't leave them in grams. I need a unit that represents an amount of atoms or particles. Moles is perfect. Moles is a unit that represents a quantity of particles. I have grams, and I could easily convert from grams to moles. I'll just set up a proportion. Cancel grams, we want moles. 1 mole of potassium on my periodic table is 39.10 grams. And then we just do the same thing for each. Cancel grams, we want moles. 1 mole of nitrogen is 14.01 grams. And then I'll do the same with the oxygen. We want moles. 1 mole of oxygen is 16.00. So for each one, I'm just going to divide across, and leave at least a couple sig figs, decimal spots. I guess my originals all have about 4 sig figs. So maybe 0.9890 moles of potassium. 13.85 divided by 14.01. 0.9886 moles of nitrogen. And the oxygen, 47.48 divided by 16, 2.968 moles of oxygen. Excellent. I like what I see. I have numbers that are really close to whole numbers. And I would feel pretty confident saying that this is a ratio of 1 to 3. What do you think? Do you feel comfortable enough to put this down as, here's my formula, KNO3. Look at that. This is approximately 1 mole, approximately 1, and that is really darn close to 3. And that's what we're looking for, this whole number ratio of moles, which is a unit that represents a quantity of particles. That mole ratio then is the ratio of atoms in your formula. There should be 3 times as many oxygen atoms as nitrogen and potassium. This is potassium nitrate. There's your formula, your empirical formula, your simple whole number ratio, 1:1:3. Now, to be honest with you, I probably could have gotten that without doing any calculations. So you're thinking, wow, I just wasted all this time, right? Oh, of course not. If these are ionic, they always have a positive ion and a negative ion. The positive is always the metal. So I know that potassium is always +1. That's my metal, my positive ion. Then you're going to have some kind of nonmetals. If there's only one nonmetal, you could just find its charge on the periodic table and boom, you got your formula. If you see 2 nonmetals, I would put money down, it'll end up being a polyatomic ion. Like if you see nitrogen and oxygen, I bet it's nitrate NO3. And this should make sense. Nitrate NO3 is -1. That is the formula of potassium nitrate. If you saw potassium sulfur and oxygen, I bet it'll end up potassium sulfate, SO4. Or if it was potassium carbon and oxygen, I bet it'll end up potassium carbonate, potassium and carbonate, CO3. So you can kind of judge if your final formula is on the right track, especially if the metal only has one possible charge. So we'd be talking like a group 1 alkali metal or a group 2 alkaline earth. They always have the same charge. So you can kind of figure out the formula. Maybe not always the case, however. What if we were looking at something like this? Now these are real common. This first one is actually really similar to what we're going to end up doing in the lab. There is a compound that's 88.8% carbon, copper, and 11.2% oxygen. Well, now this one's a little tricky because copper is a transition metal and it has multiple charges. So you can't just tell me, hey, it's a copper oxide, go write the formula. Whereas the last one, let's say it was potassium and oxygen. I could write you the formula without doing any calculation. Potassium's always +1, oxygen is always -2, it's done. But I can't do that with copper. I don't know the charge. So we have to do some calculations. Alright, so if I had 100 grams of this compound, then it would be 88.8 grams of copper and 11.2 grams of oxygen. Awesome. I need to change those into moles. Moles is a unit that represents a large quantity of particles. The ratio in a formula is a quantity of particles. Cancel grams. We need moles. 1 mole of copper is 63.55 grams. And then we do the same with our oxygen. 1 mole of oxygen is 16 grams. Some of these masses are so common, like carbon, oxygen, hydrogen. You use them so often that I bet you'll memorize it. Oxygen, 16.00. Not that you're trying, it just happens by accident. All right, let's plug these in our calculator. We'll leave maybe 3 sig figs or so. All right, so 88.8 divided by 63.55. I'm going to go 1.40. There's the copper. 11.2 by 16. Ha! I love it. 0.700 moles of oxygen. All right, this is great. So in the last one, we ended up with whole numbers right away. Or they were at least really close to whole numbers, and we could round. I mean, we got like 0.9898, 2.9. This is close enough to round to the nearest whole number. Not the case over here. These are not whole numbers, and they're not close enough to round. However, do you see the ratio? Can you see the whole number ratio? There's twice as many moles of copper, which means in the formula there's twice as many atoms of copper. So I would put money down that this formula is Cu2O. Now, if you weren't sure, the first trick to try, if you got like weird moles, divide them by the smallest. Because you know that's going to give you a whole number then. At least one of them is a whole number. Try doing that to both. 0.700, which like this one's obvious. We know that it's a 2-to-1 ratio. But again, if you had some kind of weird numbers, that's exactly what I would do. That's not a 7. Divide them both by the smallest. 0.7. And then this would give us our 2. 2-to-1. Perfect. Now, other things they might ask me, they could say, what is the charge on the copper? What form of copper is being used in this compound? And I would say, okay, I know oxygen is always -2. Since there are 2 atoms of copper, I need to get a +2. Each must be +1. So if this were multiple choice, maybe instead of it being what's the empirical formula, they might say, what is the charge on the copper? What form of copper is being used? Or maybe they would ask me, what is the name of this compound? And I could say this compound is copper, Roman numeral 1, oxide. The Roman numeral is the charge, not the subscript. There are 2 atoms of copper for every 1 atom of oxygen. But then to make it neutral, each copper must be +1. Okay, so we could have done that on this previous question too. If you weren't convinced, you could go back and divide all these by the smallest. 0.9886. 0.9886. 0.9886. You could totally do that. And it will just confirm the ratio 1:1:3. But these will be close to round. Not a 0.4, not a 0.7. Then you got to divide by the smallest. All right, let's try one more. I like this one. Very similar. Copper is now switched for iron. 30% iron, 70% iron, 30% oxygen. Now the only thing I don't like about this problem is that you're not given a lot of sig figs to work with. I'll get over it. So let's say 100 gram sample so that I have 70 grams of iron. and 30 grams of oxygen. I need these in moles, so we'll cancel grams, put them in moles. 1 mole of iron is 55.85 grams. And there's my oxygen again. I want moles. 1 mole is 16 grams. Okay, so for sig figs, I'm going to plug this in my calculator, but I definitely don't want to just leave 1. A 70 with no decimal spot is 1 sig fig. So I'm going to leave something. It's not really your final answer here when you calculate moles. So I usually just say, leave something that seems reasonable. Maybe like 2, 3 sig figs, 2, 3 decimal spots. See what you get in your calculator and leave something reasonable. So maybe like 1.253 moles of iron. And then let's see what we got for oxygen. 30 divided by 16, 1.875 moles of oxygen. These are not whole numbers and they're not close enough to round. Even that 1.87, not close enough. Maybe a 1.97, but not the 87. So we got to try our first line of defense. Divide them both by the smallest. I mean, and again, sometimes you can estimate the ratio. Like this earlier one, we kind of knew, oh yeah, it's like a 2 to 1. This one's kind of goofy. I know it's not 2 to 1. So I don't really know what this one's going to end up being. Let's plug it in. If I divide by the smallest, I'm guaranteed a 1. And then we do the same thing here, 1.253. Ha! Okay, I can do this. 1.496 blah, 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 which is approximately 1.5. Okay, so this actually confirms kind of what I was thinking. I knew that it would be less than 1 to 2, a ratio of 1 to about 1.5. Which now we just ask ourselves, how can I make that a whole number ratio? I still can't write a formula that's FEO like 1.5. But if you get something like this, I bet you'd all say, just multiply by 2, right? And if you do it to 1, you have to do it to both. We have to keep the ratio consistent. So instead of a ratio of 1 to 1.5, we'll say 2 to 3. So here's where you just want to leave enough precision in your moles that you get something reasonable that you can make a whole number. If you were to round that just to like 1.3 or 1.9, you're not going to get a great ratio. So leave at least like 2, 3 decimal spots, something along those lines. These moles I will not mark wrong. This isn't really your final answer. So I'm not going to take off for sig figs on these mole calculations. Really, your final answer is the formula. Fe2O3. Oxygen is always -2. That gives me a -6. This must be iron, Roman numeral 3 oxide. And they're not asking me on this particular problem, but they could. On a test or a quiz, what is the charge on the iron? What is the formula of this compound? What is the name of this compound? There it is, empirical formulas. They're kind of fun. Assume a 100-gram sample, so you can use your percentages as masses. Turn grams into moles, because moles represents a quantity of particles. Then we're going to look for a whole number ratio of particles. If it's not a whole number right away, always do this first. Divide by the smallest. Often that'll fix it. And if not, maybe you get something like this, 1 to 1.5. Multiply by 2. 1 to 1.33333. Multiply them all by 3. You can probably make whole numbers out of them at that point.